So here's the last part of the 7.1 lecture before we jump into the 7.2 lecture, and it has again this common theme about net change. And let's just remind ourselves the idea that net change can be thought of as an integral of some rate over time on some beginning and end point in time. So the pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. The rate in gallons per minute at which the pump operates is recorded at 5-minute intervals for 1 hour. How many gallons were pumped during that hour? Well, this rate is like our f prime. Let's give it a name. Let's call it f prime, and it is a function of t. For some given time, I've got different rates. If I want to figure out how many gallons were being pumped, I'm asking, well, what is the integral from 0 to 60 of this rate function, of this f prime function over that time? Now, we have a choice. We don't actually have a function that we can find the antiderivative of. But, you know, that's the way life is sometimes. You're longing for something to take the antiderivative of, and it's just not there for you. But it does indeed. So what can we do? Well, we can estimate the value of this antiderivative by using a Riemann sum. Now, how many different Riemann sums do we know about? I know of 5, right hand, left hand, midpoint, trapezoidal, and Simpsons. Which one do you want to use? The ones that has the sort of the best combination of easy and accurate is trapezoidal. The one that's got the game winner in terms of accuracy totally is Simpsons. So if you want to use Simpson's method, we could review it right now. If you want to use trapezoidal, which is more likely to show up on the AP exam, we can do that right now. Trapezoidal it is. All right. So the trapezoidal method, for each of these areas, we're going to picture a trapezoid. The trapezoid has 2 sides. One is the height of the rate at 0. The next one is the height of the rate, the rate at 5 minutes. And we end up getting a trapezoid with a area of, well, what's the area of a trapezoid? 1/2 B1 plus B2 times H. Well, in the very first trapezoid, it has a height of 58. The second base has a height of 60. And these are the 2 bases, and this particular piece right there, that's the H, the height. It's kind of like laying on its side. And it's got a height of 5. And there's the first trapezoid done. Second trapezoid, 1/2 60 plus 65. Its height is 5 again, plus 1/2 65 plus 64, and the height of that trapezoid is 5, plus 1/2 64 plus 58 times 5 plus 1/2 58 plus 57 times 5. You get the picture. Okay, that is each trapezoid explicitly being written out. But what did we learn? We can factor out a 5. And if we distribute the 1/2 through each one of those terms, we end up with a 1/2 of 60 and another 1/2 of 60. We get a single 60 out of that. We get 1/2 of a 65 and the other 1/2 of a 65. We get a 65 out of that. We end up with 1/2 of the first one plus the sum of all the other ones, 60 plus 65 plus ... up until the second to last one, 63. And then the second to last one's there. And then with the very last one, a 1/2 of that. So our final answer will be 5 times 1/2 of 58, add up all those numbers, and 1/2 of 63. And that will give us the trapezoidal estimate of the area under that curve based on that data. And I know you're all longing to put those numbers into your calculator and add them up. I am not willing to do that. So we're just going to let it sit there. But that's the process of doing that. Is that all right? Edmund, is that going to be able to cover it for you for the other one? All right. Evan is busy putting the numbers in the calculator? Or are you working on 27 now?
No, this is 760.5.
760.5. And they say that the answer is is 3,582.5. Take that number and multiply it by 5, please. Okay. Okay, so what happened? You did take all those numbers and add them up, but remember we had factored out that 5, and then you multiply that whole thing by 5. All right. So that's the end of the 7-1 lecture. All right.